Now, I can't leave the story without saying one last thing. It's not that we understand there's a neutron and a proton and an electron, but it's where the electron is. As a matter of fact, understanding that determines all the properties of a substance. Where the electron is, because the electron's on the outside, they're the first things to run into another atom. Matter of fact, where the electron is also determines the shape of the molecule, which gives it medical properties, properties that you want it to have in terms of the clothing, whether it can allow breathability or stops water from it. All that is determined where the electron is. So, we're going to study that in these next sets, and this is almost all mathematical, was the heroes of the day here. And this is the 1913 to 1930. The descriptions are all happening 10 years after they discovered the electron, the neutron, and the protons in the process. So one of the things that was the key is that the jumping of electrons from an outer level to an inner level, from 5 levels out to 2 levels out, 4 levels out, 2 levels out, 3 levels out to 2 levels out, gave off a certain amount of light. Niels Bohr was studying that. He was a student of Rutherford's and went off to study this himself. And he realized that he could calculate how far that electron was. Just like a satellite might orbit a planet, and if they're closer or farther, they have different potential energies. He was able to calculate what energies they have and what that meant in terms of distances to the nucleus. So he came up with this Bohr atom of the model of the atom, and he said, jumping between these gives off distinct amounts. If you jump a smaller amount like this, that's red light. That's less energy than jumping 2 levels from 4 to 3, and it's still less energy from jumping 5 to 3. And so the light that we were seeing in those spectra were because the electrons that were excited because they got heated or got bumped in by another electron or by another atom that caused the electrons to get bumped out would give off their own light. That light depends on how far the electron was jumping. And since every atom had a different set of electrons, they would give off their own colors of light. Now, what you see here is that here's the visible spectrum. He was also able to look and he saw that there's some infrared lights that are coming off and ultraviolet lights. What were those? Well, the lights that fell down to the closest level to the nucleus were even further higher energy light, so that's the ultraviolet. That's what we suntan with. Okay? The visible light is what we can see and what causes the rainbow. And then if you fall down instead of to the second layer but to the third layer, that was given the infrared signal. So all of the light patterns were explainable because where the electron fell. If they fell further, they gave off higher energy. Fell to the second level, they gave off visible light. If they fell to the third level, it's the infrared light. At about the same time, they were still trying to figure out, gosh, you know, that's fine as a description, but anytime you take electrons and you move them back and forth like in an antenna or in a radio station or a television station, they broadcast out energy from them. Moving electrons back and forth causes them to broadcast energy out as wavelengths of light or radio waves. So de Broglie was saying, I don't understand why that's not happening for the electron. He thought of them as a natural frequency of vibration. And so when he was looking at the light, he said, what if the light is vibrating around an equilibrium point where it naturally likes to sit? If that was the wave that that electron could have, and its vibration was the exact number of wavelengths, then it would be like a wave passing through the bridge that fell apart because the wavelength is the same as that path. And he was able to say, you know what, if I took a place that had this as one wave in it, that's the path that would have one complete up and down, except instead of being like this, okay, from here to here, it's going to go around in a circle. So here's the wave at its peak, goes through its trough down here, and it comes back to its peak up there. That's one wave. Peak, trough, peak, trough, and back again. So that's one wavelength. There's this path in the middle. 2 wavelengths that fit in. Here's the two peaks right there and right there. This one has 3 peaks in it, 4 peaks in it. And he said as long as an electron can travel around that path and still make it up and down as a wave, then that would explain these circles that Bohr had seen. And then there's some mathematics that implies. Let me turn this off. Okay, so that only certain size circles would allow an electron, which has a wave nature to it, just like light had a wave nature to it, would be allowed, and then anything in between was not allowed. Heisenberg came along and said, you know, I think I can agree with that, but I'm going to treat these more like statistics, possibilities. And he just said, you know, at that distance that you're calling the path is the most likely position. It's not that it can't travel in between, but it's far less likely. And so he used some statistics approach to come up with that same sort of picture that both Broglie and Bohr were looking at. and they came up with some mathematics that described it. This is called the Heisenberg uncertainty principle, saying that I can't know the position of the electron exactly, so I have to sort of guess at it, and the best I can do is a probability. Okay? So those two were coming up with different maths and different kinds of math. This one was statistics here, and he was just using wavelengths, which is more of calculus. What ends up happening is that they do work out a set of equations, and instead of boring you with what those equations look like in terms of the numbers, using sines and cosines, here's what they look like mathematically. Now, this is going to be comparable to a slinky. I'm going to just compare you this. This slinky can vibrate as a whole like this, and especially if I make it 3D by making a circular like this. This is one wave where it's just one lobe in it. But you can also make this slinky have two waves in it, right? So I can get it to be in its natural frequency, and if I can make this go up and down, you can see this. As a matter of fact, if I make it circular, especially with my shirt in the background, you can see there's two lobes, one on this side, one on this side. Well, the same thing is happening with a single point that's vibrating around. It's being held by electric force. This is when it's vibrating as a single or a whole, like so. Okay. Here's when the electron has two lobes in it, and if I can get this to, let me see if I can do this. Especially when it's at a bit of an angle, maybe you can see that better. There's two lobes here. I don't know which is better. There we go. And that's the next phase, more complex. But that's what those equations ended up predicting. This is what we're going to learn as SPs, Ds, different orbitals like that. And so you're going to see that you can use these to explain where the electron is. So that was the last step. Pauly gets in there and he's saying, there's a rule. Not only can the electrons travel in these, but only a certain number can travel in those. And once they've filled up one of those shapes, you have to move on to the next one. And that's what we're going to learn in the next video.